So we'll be talking about several ways to integrate some different integrands, and so we'll discuss a variety of integration techniques in the coming sections. It's a good idea to take pause here and review some of the basic integration techniques and some of the basic formulas that we've already looked at. So what you see over here is a table with some basic integrals. Most of these you learn to integrate by knowing what the antiderivative is, so just guessing it from knowing the derivative. For example, you know that the derivative of sine ax is a cosine ax, and so you could guess the integral of cosine ax is 1 over a sine ax, right? And so that's just knowing the antiderivative. This here is a constant. Also, these you know from guessing the antiderivative. Similarly with these, you could guess from the antiderivative. You could also look into doing trigonometric substitutions. Over here, we could solve for the integral of tan ax via substitution, integration by substitution. Similarly for cotan, and we'll also look at how to integrate secant by basically multiplying by 1. And let's go ahead and review some of these integrations. So here we have substitution, and we'll move quickly because this is a review. You could see that tangent, you could break it up into sine and cosine, and then you notice that, well, the derivative of cosine is minus sine. And so that's primed for u substitution, because once you take the derivative, so if u was cosine, the derivative is going to be negative a sine, and so you could sweep up that sine dx under the rug of du, and we have that extra minus sign coming from there. And you integrate. You could also strategically multiply by 1, okay? Seems kind of odd, but you could simplify a lot of things by using this trick. So secant, multiply secant by 1, you know, that's true. Secant ax times 1 is secant ax. But 1 is expressed in many different ways, and one way to express 1 is this ratio there, okay? That ratio is 1. But when we distribute that ratio, we can write out terms that are that we could strategically use u substitution with. So if you take u to be the denominator, du is this term, which you could sweep up that whole term there under the rug and get that result right there. And now I wouldn't feel too bad if I did not realize that once I first looked at secant. You know, it's one of these tricky things, and that's a challenge in this class, that a lot of the integrals are basically done through a variety of techniques. Nevertheless, with a lot of practice, we can get a good idea of how to integrate a particular integral. Let's take a look at this one here. This is subtle substitution, okay? Subtle, you'll see why. Now you take a look at this. One of your first instincts is to sweep ex plus e to the minus x, you know, under the rug of u. But if you do that, you don't quite get a du that's, you know, that's that'll help us out in integrating. And so one trick is that we can multiply by 1 again and distribute that e to the power of x. And you know, here you may think, well, you know, let's sweep e to the 2x plus 1 under the rug, and that still doesn't quite work, okay? But what you can do is use a u substitution with u is equal to e to the x, and then this becomes u squared. I mean, notice here where the trick is occurring. I mean, u is e to the x, so when you square u, you're going to get e to the 2x, okay? That's just one of the properties of exponents. And so you could write this e to the 2x as u squared, And we can keep this in mind, you know, with exponents. It's an interesting trick. And from there, you can integrate this. You just remember the what the derivative of arctan is, and substitute back the expression for x, and you're done. Another basic integration technique is to split up fractions, just taking advantage of the simple property that a plus b over c is equal to a over c plus b over c. Of course, this would not work if we, you know, switched up the numerator and denominator here. You know, you can't sort of distribute a fraction that way, but when the numerator is a sum, you can. And so, taking advantage of that, we could break this up into fractions and do two separate integrals. And with the cosine squared, we could take advantage of the half angle formula to write that out. And with the sine cubed term, we could also use u substitution for that integral. Okay, it's primed with having this cosine x dx for u substitution. That du is cosine x dx, and we do the integral and we end up with that term there. Okay, and by the way, that cosine x came from the 1 over secant. Some more tricks. Division by rational functions. So here you just use long division, okay, to break this, to simplify this integral into a polynomial and remainder, okay. And here I carry out the long division for you. You know, how many times does x go into x squared? It goes in there x times, and so x plus 4 times x is this term here. Subtract that term from the original term you're dividing from, and you get minus 2x minus 1. And then how many times does x go into negative 2x minus 1? Well, it goes in there minus 2 times, and then x plus 4 times negative 2 is negative 2x minus 8. Subtract that from what we were left with here, and you get 7. And so now, you know, x doesn't go into 7, and so you have a remainder term there. So you get x minus 2 plus 7 over x plus 4. And you could review long division. There are several resources there that are really helpful. So, okay, you could then integrate that term much more easily and this term much more easily, and you get that result there. Okay, you can integrate this using u substitution, or frankly, you could have just guessed it from the antiderivative. Finally, another basic integration technique is completing the square. Okay, and now if we have a term that's like this, and I'm noticing that in my notes it's missing, that should be an x squared there. Okay, so minus x squared minus 8x minus 7. Well, we complete the square, which basically means you want to sweep, you want to kind of get rid of this term and write this polynomial as something like, you know, x plus something else squared. Okay, so you know, you'll have a perfect square there. Okay, and now you can't get a perfect, you can't quite factor, so we can't take this and we can't take that term x squared minus 8x minus 7 and write it exactly like x minus a squared. It's not a perfect square, but we can do it if we include an extra parameter there. So we could, so how do we do that? Well, we have an 8x term. Okay, we have an 8x term, so whatever we put into the perfect square better sum up to give us that 8x term. First, you know, take out that minus sign, factor out that minus sign, and 4 plus 4 will give you 8x. Okay, and so you can add and subtract 16. That's just 0, right? Plus 16 minus 16 is 0. So from 0, we create plus 16 and minus 16. Why do we want 16? Well, because 4 plus 4 is 8, but 4 squared is 16. Okay? And so this idea is called completing the square. And now with this term, that term there is x plus 4 squared. Okay? And you could see, rather than having x squared plus something times x, we just have a x plus a constant squared. Okay? And that could simplify our integrand. And negative 16 plus 7, well, that's minus 9. That's sort of what's left over in the perfect square. Okay? And so doing that, we'll get 9 minus u squared. And there you could sort of remember the antiderivative of, well, you'd have to do one u substitution, then you remember the antiderivative. You'd remember the derivative of arcsine, and you could guess that that's the antiderivative of this term is arcsine, and you end up with that final expression there. So for this one in particular, I would factor out that minus sign, and so just have a plus there for everything. And then notice that when you distribute this, you'll get an x squared minus 2ax plus a squared plus b. Okay? And so from that, you know that this needs to equal 7. Okay? The a squared plus b. And this 8 needs to equal minus 2a. Okay? And so you'll have, looking at that, you'll have minus 2a is equal to 8, which gives you that a is equal to negative 4, which is correct because x minus negative 4 is x plus 4, and that's what we have there. And you then, with that being said, you also have this term here. You'll have then a squared plus b. That needs to equal 7. And you already solved for a. That's negative 4 squared plus b. And so you'll get 16 plus b equals 7. And that will give you a b of negative 9, right? 7 minus 16 and negative 9. And so that's the idea of completing the squares. Just reviewed that for you really quickly there. I should also remark that this was a minus sign there, okay? But we factored that out early on. And so what's left then is to just find the parameters a and b. Some people might put a plus there, but it's up to you how you want to define those parameters. And if you have an overall constant multiplying the x squared, it's a good idea to factor that out in such a way that you just get x squared there. So if there was like 2x squared minus 8x minus 4, you just factor out 2 from each of those terms, and you'll be left inside the parentheses with the x squared plus other terms, and then you could carry out that completing the square.